Welcome back, everybody. Second to last chapter of the semester. We're going to focus on this idea of the evolution and the distribution of galaxies. Similar to chapter 27, this is a relatively short chapter. And like chapter 27, it's packed filled with a lot of high-level ideas that are difficult to kind of grasp the first time around. So don't feel kind of bad, don't feel ashamed if you have to read this chapter a second time around to get a full appreciation for the ideas that are discussed. It's kind of natural, put it that way, kind of like puberty. This is natural to have to do a second time, admittedly. But this picture that you see right here, I kind of call it scary eyes, but that's just the way that I see this. But this is a picture of two galaxies that are in the process of colliding. So therefore, they are evolving in a very unusual manner, the fact that they're colliding with each other. And that's going to be part of the emphasis of chapter 28 in today's lecture. But first things first is that we have to talk about this idea called look-back time. And this is something that we've, in essence, danced around for the past several chapters. But it turns out that the further away that an object is from you, the longer that it takes for light to get to you in the first place. And this is primarily because light from that object, it doesn't arrive at the Earth instantaneously. Light travels at a fast but a finite speed of, again, 300,000 kilometers per second, 150,000-ish miles per hour. Sorry, miles per second, my apologies. So if an object is very, very far away, then when it produces light in its past, that light takes a long time to get to the Earth. So that means that really when we're getting light from distant objects, we're really getting light from how it looked in the past, not how it looks in modern day times. So that's kind of where this picture comes into play. If you look at an object which is a certain distance away from the Earth, then really kind of where it is compared to where we are is that we're getting light from how it looked roughly about 2 billion years ago. On the flip side, if an object is extremely far away, then maybe we're getting light from that object as it looked 10 billion years ago into our telescopes modern day time. So the further we kind of look back, kind of the more distant that we look at an object, the younger they seem to look in this case, the kind of more unevolved the galaxies appear to be for the most part. And this is this idea of look back time. The further back that you look, the further back in the past you're looking as well. So it's silly, but we kind of need to keep that in the back of our mind, because piggybacking off chapter 27 ideas, the further away a quasar was, the dimmer it appears. That's true. But then again, the further away that it is, the older that it is as well. So that's something that we kind of softly mentioned in chapter 27, but now it kind of comes full circle in chapter 28 with distant objects being very, very old, and closer objects being kind of much younger, at least in terms of the light that we get from them in this case. But nonetheless, the next part of chapter 28 kind of focuses on a concept from chapter 25, when we talked about the Milky Way galaxy and its evolution and its growth. We talked about how, for example, the Milky Way galaxy formed from a accretion and aggregation of gas, dust, and stars. Well, it turns out that that's not the only way to form a galaxy. That's a way that we think the Milky Way galaxy was formed, but that's not true for every single galaxy out there. In particular, galaxies like elliptical galaxies. It turns out that we think that elliptical and spiral galaxies in general formed in completely different ways. And we're going to kind of talk about very briefly how they kind of differ from each other. So for example, in this top part of the picture, you'll notice that here in this kind of multiple colored sphere of gas, dust, and stars as well, we have a protogalactic cloud. And admittedly, this is a protogalactic cloud which has very little angular momentum. So what this basically means is that this particular protogalactic cloud, it has lots of mass, but it isn't really spinning in any given direction. So that means that when this protogalactic cloud is able to reach a high enough mass to allow internal collapse, to allow kind of internal gravity to collapse the cloud onto itself, due to its very small angular momentum, then just like you see here in the second picture, and just like you see in the third picture as well, the shape of this galaxy tends to be more spherical because it isn't flattened out due to having no or very little angular momentum in its initial stages, such that it eventually forms an elliptical galaxy for the most part. Spiral galaxies are a little bit different in the sense that they could have similar masses to an elliptical galaxy, but because that protogalactic cloud that they formed out of had more momentum initially in the beginning, then that initial angular momentum, that initial spinning motion, causes the galaxy to collapse on itself, but also to flatten as well. And that flattening shape eventually kind of forms those spiral density waves, aka the arms, and the actual kind of other parts of the disk structure of the galaxy as well, and eventually kind of form a SBA or an SA type of galaxy where the arms are tightly wound, the bulge is very, very large, but you formed an actual kind of spiral galaxy in that case. So depending upon the angular momentum, aka the initial rotational motion of the protogalactic cloud, then that can kind of explain how galaxies can evolve over time into forming an elliptical or into forming a spiral galaxy in this case. In a similar sense, not so much rotational motion, but just the amount of mass, this idea of density, could also affect the type of galaxy that's formed in the first place from a protogalactic cloud. So again, kind of referencing those top four pictures, if you have a protogalactic cloud that is very, very high density, then what that means off is that the higher density, it actually kind of allows for the cloud to cool down a little bit faster. And therefore that kind of cooling down ability that a high density protogalactic cloud has allows it to turn into an elliptical galaxy in most cases. On the flip side, if you look here in the bottom, you have a protogalactic cloud, which is admittedly larger in this case than the other one, that's true. But the reason that it's larger is because it has the same amount of mass, roughly speaking, but it has a lower density because it's occupying more space. It has a larger volume with the same mass, aka a lower density. That lower density allows the kind of cloud to cool off more slowly, kind of retain heat a little bit better. And therefore, instead of kind of maintaining its spherical shape, it actually kind of begins to flatten out in this case, eventually kind of forming a bulge in the center, kind of like we see right here, but also kind of forming the spiral density waves, the kind of arms and the kind of spurs that we talked about from before back in chapter 25 and 26 as well. So depending upon the initial conditions of the protogalactic cloud, this idea of angular momentum, aka rotational speed, and this idea of density, aka kind of internal gravity, they allow us to kind of understand how galaxies can evolve, can come into existence in the first place, which kind of deals with the evolution aspect of galaxies within the universe. But it turns out that irregular galaxies and also ellipticals as well, they can also be formed through the process of galaxy collisions. And what you see here are 5 different pictures of different colliding galaxies. So they're not the same 2 galaxies because the galaxy collision process takes a lot longer than a human lifetime. So there's no way that we've actually been able to capture one in real time. But these show 6 different galaxies in different states of collision. And the key thing about collisions is that we know that we're dealing with galaxies that are colliding due to telltale symptoms, telltale features that they have. The first of which is the structure that I've highlighted here in red. You'll notice that here in figure 2, there's an empty void between the 2 galaxies. Whereas here, that void is kind of filled in by a very thin collection of gas that is really kind of coming from the disk, the spiral density waves of both of those galaxies. And those are called bridges because they're collections of gas that bridge together the actual disks of both galaxies. On the flip side, this little kind of piece that you see right here kind of protruding off of the disk of what was once the left side galaxy here, because it's now kind of detached and really unwound from the disk structure, we call that a tidal tail. Kind of like this guy right here is a tidal bridge. And why do we call it tidal? Well, it deals with tidal forces, aka differences in gravity, like we talked about, for example, with the tides here on Earth, for example, back in chapter 4. So the shape of this kind of collection of gas is just basically similar to that of a cat tail or a dog tail in this case. But the key idea with this one, though, is that it is a process of galaxy collision, that gravity between the two objects rearranges the material within those two galaxies, producing the tidal bridges in red and now tidal tails highlighted in this kind of golden yellow circle right here. It turns out that in figure 5, starbursts, not the candy granted, but starbursts occur as well. And the reason why is that when you start to have the actual kind of two disks merge together from figure 4 into figure 5, what happens is that you have a lot of gas and dust that is now occupying the same space or in close proximity to each other. And all of that new material within the now singular blob-looking disk in figure 5 right here, it creates ideal conditions for molecular clouds to form. This idea of stars to begin forming in high amounts. So star burst just kind of literally means a burst of star formation, or another way of saying that is we say the star formation rate within this galaxy, technically two of them colliding, but within this galaxy has increased due to the collision, creating a starburst event as a consequence. And the last kind of feature that we can see in astronomy that gives us evidence of colliding galaxies, aka evolving galaxies, are this idea of tidal shells. And admittedly, it's kind of hard to see right here, but you can kind of see a tidal shell and kind of like an echo of one, so to speak, right here. But this guy right here, and to a lesser extent, this guy right here, these are tidal shells that are formed from, again, the internal redistribution of gas, dust, and stars within merging galaxies. But these tidal shells, these tidal bridges, these tidal tails and starbursts, they can occur very visibly during the galaxy collision process. And so by kind of seeing these features, primarily the time of tails, bridges, and shells, they give us very strong evidence for galaxy collision and therefore kind of active galaxy interaction, this idea of galaxies evolving in a very kind of chaotic, violent type of manner. But still, chapter 28 is all about the evolution and distribution, but right now we're focused on evolution of galaxies, how they change over time. So turning into an elliptical galaxy is part of evolution, but also kind of merging with another galaxy is also a form of evolution as well. So what we're going to say is that in regards to mergers of galaxies, we're going to say that mergers affect morphology. It's a very cool saying that my advisor taught me long ago when I took this class and its equivalent back in the day. But this kind of shows us here computer simulation of two galaxies that are merging. And you can kind of clearly see that when they're far apart, there might be a thin, tenuous connection between them, but the connection between them is clearly visible as a tidal bridge right here and here. And we can also see the kind of tidal tails that have formed in these successive 4 images. And now you kind of see in this area here, we start to see this idea of kind of tidal shells, and the very kind of bright colors that we see going on right here kind of correspond to starburst activity, basically. And the very end is that maybe you have an irregular galaxy, maybe you're lucky and you get an elliptical or a lenticular galaxy, the SO type that we talked about with the Hubble tuning fork. But the idea here is that during a collision process, which is actually quite common, compared to, for example, stars colliding, which is quite uncommon, as we'll find out shortly. But during the collision process between galaxies, the gas, the dust, and the stars, the mass within the galaxy gets redistributed, pushed around, and perturbed, aka disturbed, as a consequence of the gravity between the two objects. And it turns out that it kind of creates the spiral bar, aka this kind of bridge between the two galaxies. It enriches the two disks of the galaxies, or just enriches the gas and the dust and the stars within the galaxies. And in the process of producing tidal tails, it can remove some of that gas and dust as well. What this basically means is that this kind of gives us tangible proof that the Hubble tuning fork, unlike what Hubble thought back when he created it, cannot be used to gauge the age of a galaxy. Because, for example, if you're looking at a galaxy right here that kind of looks like maybe it's an elliptical galaxy, it looks very rough around the edges. So maybe you would be kind of inclined to think that, okay, well, maybe this is a very kind of old galaxy to where it's kind of pushed, pulled itself apart. It's very kind of amorphous. But this could actually just be the result of a galaxy collision between two young galaxies that has kind of prematurely aged them as a consequence of this process of mergers affecting morphology or shape as a consequence. So the Hubble tuning fork, this now gives us definitive evidence. Even though I did mention it back in chapter 26, it gives us definitive evidence now that we can't use the tuning fork as kind of like a predictor of age based on appearance in this case. The age of a galaxy has to be determined in other ways, not just on physical appearance, sadly, in this case. But it turns out that the process of collisions is also referred to sometimes as galactic cannibalism. Because back in chapter 25, when we talked about the Milky Way galaxy, we said that the Milky Way galaxy has kind of already absorbed two galaxies, or is in the process of absorbing two other galaxies, two other dwarf galaxies, smaller galaxies in comparison. And it's in the process of merging with two others, and also the Andromeda even further out as well. But the key idea is that one galaxy will kind of emerge from that collision, from that merging process, and therefore two have become one, and therefore we refer to that as galactic cannibalism. But it turns out that, again, galactic cannibalism can be a good thing because it stimulates star formation. It increases the star formation rate within the two galaxies. And maybe that star that is formed might form a solar system around it that might have life, aka us, for example. Now, there's no evidence of that, but it's an interesting idea. It's an interesting kind of conjecture to kind of put forth that maybe our Milky Way galaxy was formed in a bout of starbursts activity when the Milky Way galaxy kind of combined with the Canis Major galaxy, for example. Not a guarantee, no proof, but interesting idea to talk about nonetheless, that our birth is the result of the death of another galaxy. So anytime that we see mergers, it's an active case of galactic cannibalism. So the universe can be a very mean place, but it turns out that there is some good that comes from this in this case. Now, this kind of next idea is going to build off of chapters 26, to a small extent 27, but also this idea of how galaxies evolve over time, this idea of what we're going to call the cosmological principle. And the base of the word cosmological is the word cosmology, and we'll kind of see that word in chapter 29 very shortly. But cosmological, aka the cosmos, is basically kind of referring to everything in the universe. So the cosmological principle is a principle, a law, something that's been well tested in this case, that involves the entire universe in some manner, in some shape. And based upon Hubble's research back in chapter 26, Hubble discovered that when he looked for all of these distant galaxies in different directions in the nighttime sky, he basically determined that the number of galaxies that he saw in every part of the nighttime sky were the same. Now, admittedly, they're similar. I'm not going to say that they're the same, but they are surprisingly similar, even though his kind of observations had a problem. And that problem dealt with the fact that when he was looking at galaxies within the line of sight of the disk of the Milky Way, light from those galaxies has to travel through the dust and the gas in the Milky Way's disk. And just like we talked about in chapter 21 in the formation of galaxies, when light travels through dust, it undergoes reddening, aka certain colors are removed and only the redder colors kind of remain. So therefore you're getting an artificial perception of that object. It's older than it appears, sadly. But nonetheless, Hubble's research told him that the number of galaxies was basically the same in all directions, and he's basically correct. And what he kind of recognized is that because of that observation, what that means is that to any observer on the north or the south pole of the Earth, the universe is the same in all directions, and that means that matter is evenly distributed in terms of large-scale distribution of our universe. Little small pockets, maybe not so much. But if you're looking at large-scale kind of superclusters and things like that, Hubble just figures out that, the universe looks pretty much the same in all directions. So what he concluded, what he stated, is that the universe, in terms of galaxy population, matter and energy population, it is isotropic and homogeneous. Now, you might have heard the word homogeneous before. Isotropic, probably not. But let's go ahead and kind of take a look at what these two words mean before moving on to their idea and applications. So here are two pictures. And what we're going to say is that the picture on the left corresponds to several of these kind of red bricks. arranged in a circular pattern. And what we're going to say is that the pattern of red bricks on the left, it is a homogeneous arrangement of bricks, but it is not an isotropic arrangement of bricks. On the flip side, the picture that's on the right-hand side, these kind of little black lines that are all emerging from this black dot in the center, we're going to say that this corresponds to an isotropic pattern, but it's not a homogeneous pattern. So to kind of understand the differences, let me go ahead and kind of start off with the right and then work my way to the left. So when we say that something is isotropic but not homogeneous, isotropic means that if you start from the center and move away in a single direction, then what you're looking for, in this case matter, is the same in that one direction. So that's what isotropic means. Homogeneous, okay, it means that it's the same at all locations. So for example, if I kind of look at this point right here, there is a black line at this location. So there's ink at this spot right here. But if I move a little bit up, there is no ink at this location. And because there's no ink at this location, then that means that we are not homogeneous. However, if I kind of go here to the left, if I move to this location, there's a brick. If I move to this location, there's a brick. If I move to this location, there's a brick. So there's a brick in every location. So therefore we are homogeneous. We kind of are the same in every little small part of the universe. But isotropic means that total amount, or kind of amount, is the same in a single direction. So for example, the amount of black ink is the same here as it is up here as well. So all of these black lines are the same compared to each other. So therefore they're isotropic. The problem with this one on the left is that I kind of go to the left right here. Let's try again. 1, 2, try that again. 1, 2, 3, 4 and a half blocks. But if I go here, 1, 2, 3, 4, 5, 6, almost 7 blocks if I go at an angle. Whereas here, this black line is the same as this black line right here. So I get more blocks going on a diagonal. I get fewer blocks going horizontal. And therefore, because those aren't the same in that straight line direction, then that means that we're not isotropic. We're not the same along each direction comparatively, but at each location individually, we do have a block present. So therefore, homogeneous but not isotropic, isotropic but not homogeneous. But it turns out that based upon Hubble's research, our universe is both homogeneous and isotropic. Each individual portion looks the same. When I look in one direction, compare it to another direction, they look the same as well. So the same on small scales, the same on large scales, and that's what the cosmological principle states. But the really cool thing, though, are the consequences of the cosmological principle. Because the universe is isotropic, that means that it's the same in all directions. And if it's the same in all directions, and it's also homogeneous, then the consequence of that is that the universe doesn't have a visible edge. Because if the universe had a visible edge, then it would look different. It would look not homogeneous in that direction. But it looks homogeneous in all directions, according to Hubble and those who came after him. So the universe doesn't have any visible edges. Well, if the universe doesn't have any visible edges, that means that it has to be infinite in size, and that's mind-blowing in and of itself. But the weirder consequence is that the universe has no center. Let that sink in for a second. Now, when you think about that, you're like, wait. Everything has a center. All right, well, riddle me this. How do you find the center of a piece of paper? By looking at the edges and by finding a common distance from two opposite sides. That is the center of that object. But if there are no edges, then you can't use those edges that are not there to find that equidistant point from two opposite sides. So without edges, there's no center. And because we don't see any visible edge to the universe, because it's homogeneous and isotropic, it has no center and it's infinite in size. And that is truly mind-blowing. But this is the consequence, a really weird one, but this is the consequence of the cosmological principle. Everything looks the same in every direction, so therefore it's the same literally everywhere, infinite in size. And if something's infinite in size, it has no edges, and therefore it has no center. Weird, but that's the principle, and that's the consequences of it. So here's kind of a computer simulation hand drawing combination, which showcases the homogeneity and also the isotropicness of the nearby areas, the kind of nearby collection of superclusters that are surrounding our own. So again, just kind of as a quick reminder, this is not taken from a satellite. This is just a computer simulation here. We are part of the Virgo supercluster, kind of right here in this region. And the key thing about that one is that in the other superclusters that are around us, they're evenly spaced. And then there are some voids. There are some kind of areas where there is nothing in the universe. But you'll notice that they're kind of pretty well spread out. They're not quite uniform, but they're surprisingly close. So this just kind of shows us a picture of all of our nearby superclusters, of which there are many of them. And they're all more or less uniformly spread out. And no matter kind of where I go relative to the Virgo supercluster, they're kind of the same essentially in all directions. So this is an alternate understanding of this idea of the cosmological principle. I like this one best. The other one that I showed you before was cool, don't get me wrong, but I kind of like this one best. It's my personal favorite. As you can see right here, this is a false color image. This is not what the universe actually looks like to a telescope. However, this is called the 2MASS, or the 2 micron all-sky survey. 2 micron because that's the wavelength of light they were looking for. And what you'll notice here is that this is from the 2MASS satellite. It really was looking for infrared sources of light throughout the entire galaxy, and it collected all this data over a very long period of time. But by assigning colors to different intensities and slightly different wavelengths as well, what you'll notice here is that this kind of turned into an elliptical shaped picture. It shows us that on very large scales, looking at very large redshifts, aka very far distances away from our own galaxy, we'll notice here that all objects that emit infrared light at 2 microns, which are other galaxies and other phenomenon as well, they're mainly kind of clustered. There really aren't any big black patches. There are some voids here and here, and a little bit of a void right here as well. But there isn't a large patch of solid black in the kind of area around our own kind of galaxy right here. So this picture just kind of gives us further proof of the cosmological principle that galaxies have evolved over a long period of time to where they're more or less kind of uniformly spread out, and therefore we kind of have a uniform density of galaxies. Okay, well, this right here is another computer simulation. And what this computer simulation kind of shows us is how our galaxies evolved, how our superclusters evolved over time, starting with a long time ago in the past. Now, how long ago? I'll have to wait to chapter 29 to tell you about that. But a long time ago in the past, the symbol of Z corresponds to redshift. And again, the larger the redshift, the further away the object, aka the older it is, due to the idea of look back time and how long it takes for the light to get to us in the first place. But for very large redshifts, when the universe was very, very young, everything was more or less kind of spread out, and therefore there was very little kind of voids in the universe. Everything was kind of spread out uniformly. But due to something that we called gravity, things started to clump together to form superclusters, to form groups and galaxies and solar systems and stars and planets and so on and so on and so on. So we'll go ahead and watch this computer simulation that'll help us to kind of see this idea of the cosmological principle and how it kind of evolved over time and how it kind of looks at Z equals 0, redshift equals 0, aka modern day universe around us. So those kind of little blue shapes that you see kind of forming, coalescing, those are called filaments that contain individual galaxies. And you see that even though there are kind of gaps and voids in between them, the filament structures that you see here inside this cube that we're kind of modeling, pretending is the universe, they're still more or less uniformly spread out. And they kind of started off as big clumps of gas, dust, and individual stars in the very beginning, but now they've kind of correlated or kind of coalesced or kind of accreted into galaxies and groups and superclusters, but they still kind of obey the cosmological principle in this sense. They're more concentrated, that's true, but they're spread out essentially kind of equidistant from each other to form this nice uniform density idea in terms of galaxy evolution and galaxy location as well. So with that kind of being said, that's going to be the end of, again, a very short but a very kind of highly dense packed chapter of ideas. So just like with chapter 27, if you need to go back and review this chapter, don't feel ashamed. This is a tricky one. There's a lot of really high level ideas in this chapter that deal with the growth, the evolution, and possibly the destruction of galaxies via mergers. But once you're ready with this, then go ahead and move on to the last chapter of the semester, chapter 29, because we're skipping chapter 30. And this chapter is going to be about the culmination of the past several chapters in terms of both past, a little bit of the present, but also a lot about the future of our universe as well. Thank you for listening. Talk to you soon.